Extreme physics.
All right, let's take a look at a situation like this, where we have somebody standing on the Earth. That's awfully large for a person, but I'm drawing them large enough so that we can see them. And when you're standing on the Earth, you are actually, from a gravitational standpoint, since we are interested in the gravitational attraction between the centers of masses of two objects, you are actually one Earth radius away from the Earth. Okay, so I'll call that R. All right. Now, if we wanted to know, you're being attracted at this point. There's a force of gravity pulling you down like that. All right. And then there's a force of gravity of the Earth that you are pulling up. Okay. So there are two forces. The Earth is pulling you down, and you are pulling up on the Earth. And we can calculate the value of that. And we've learned two ways to do that. Earlier, before this unit, he said, okay, well, the force of gravity is if I know how much stuff I have, how much mass I have, times the gravitational field strength, little g. Sometimes that was known as the gravitational field strength. Sometimes that was known as the acceleration due to gravity, depending on the situation. And, of course, we know this on the Earth, on the surface of the Earth, is 9.81 meters per second squared, at least in New York. And that will vary depending on where you are on the planet a little bit. All right, so if I know my mass, I can calculate my weight. All right, so in this unit, we learned this relationship, universal gravitational equation, and it looked like that. Now, why would we use that equation instead of this one? Because this one looks like it's quite a bit more nasty, although it's still not bad. It's remarkably simple. It just has a force of gravity between two objects. M1 and M2 is proportional to the product of the two masses divided by the distance between them squared, between their center of masses squared. And that's, we use the letter R for that, little r. And then we have a constant just so we can get our units straight. And so why would we use this one? Well, we would use this one when we don't know what g is. For instance, if someone was rather on the Earth, rather than on the Earth, they were, let's say, they were above the Earth. And let's say that their center of mass was one Earth radius above the Earth, okay? Here's the radius of the Earth, right there. And now we don't know what g is here. It's going to be different. It's going to be less. The gravitational field strength as we move away from the Earth is going to be less. So now we can't use this equation anymore because we don't know g. This is where we would use this equation. All right. Now, let's step back for a second, though, and let's take a look at this situation where you actually are on the Earth. There's a gravitational attraction. So both of these must give you the same answer. And if I call you or me, in this case, if I call this 1, I would call this, okay, so this is FG, M1 times little g. Well, if both of these are true, what must little g be? I wonder. Why don't you see if you can figure that out? What is little g if both of these must be true? I will give you a moment. Pause the video now. Well, let's take a look. If both of these are true, then we have M1 in both of these. Well, I could have drawn this simpler, but it looks like this is M1. This is the mass of you. This really must be, the two objects are the mass of person 1 plus the mass of the Earth. I'll put an E here. All right. This is, of course, the radius of the Earth squared, and that's the universal gravitation constant. And if we take a look here, we see that these all together must equal, say it with me now, G. Okay, they must be G. If both of these are true, this must be G, so then I could just write this, if all that is G, I could rewrite this as G M1, and of course that's what we had up here. So little g, the acceleration due to gravity at the surface of the Earth, is the mass of the Earth divided by the radius of the Earth squared times the universal gravitational constant. Okay, so that's where that number comes from. Now, if we take a look here at this equation, this mathematical model that describes the force of gravity between two objects, M1 and M2, separated, their center of masses separated by a distance r, we see that this is an inverse square relationship in that if we double the distance between them, since the distance is squared in the denominator, the force of gravity will drop by 1/4. If we make it 3 times greater, 3 times farther apart, the force of gravity will be 1/9. All right, well, with that in mind, it's an inverse square relationship. We're going to see that those occur very often in nature. What I'd like you to do right now is actually let's use extreme physics to graph the force of gravity between two objects separated by a distance r. What does that look like? So we're going to vary r. We're going to keep moving them apart, M1 and M2. What does this graph of the force of gravity, I better put a little g here, force of gravity versus r, what does that look like? Why don't you take a moment to graph that using extreme physics.
Pause the video now.
All right, you should have graphed that. You should have said, all right, well, I'm going to, my x variable is r, my y variable is fg. I have my relationship. It is in the right form. Y, which is fg, equals everything else. I'm going to put an extremely small value in for r, and that would be 0. But you can't put 0 in there, because if you do that, everything explodes, right? So undefined, it's 0. So we'll put a extremely small value in. And when we get a small number in the denominator, we get a really big number here. And if you put a really big number in the denominator there and square it, we will get a really small number here. All right, so we got it. We have to graph that. When r is small, fg is big. And when r is big, fg is small. And I have to figure out how to connect those. R can't be 0, so it must look something like that. Okay, that's an inverse square graph. All right, very good. Now, let's take a look at another problem. I know you did one like this in your notes, but let's review. Let's say, let's take a look at this situation. Let's say, I'm not going to redraw it. Well, I guess I could. I'm going to draw our person out here. Let's take our person, and rather than having them, I'm not going to have them r away from this. Let's say they are 3r above the surface of the Earth. All right? So the person is 3r above the surface of the Earth, and when the person is on the surface of the Earth, they have a weight of 600 newtons. All right? So they have a weight of 600 newtons. What is the person's weight in this position? Okay? So Fg above the Earth as drawn in this position, what does that equal? Why don't you take a moment to figure that out?
Pause the video now.
All right. There are two ways to do it. I know some of you may have, in order to do this, you're going to need to look up some of you may have looked up the mass of the Earth and calculated the mass of the person and then went through all kinds of calculations to figure out what is the force of gravity above the Earth. And that really isn't the right way to do it. You don't want to do it that way. That's really hard. What you want to do is use the fact that it's an inverse square relationship, that you have to figure out how much farther away are they than they originally were. Okay, so originally the person was r away from the Earth, and now they are how far away? 4r. They're 4r away from the Earth, so they are 4 times farther away than they were originally. So the force of gravity on the person will be, since an inverse square relationship, will be 4 squared, or 1/16 is great. So the force of gravity let's call this position 2, and let's call this position 1. So force of gravity in 2 equals the force of gravity divided by 4 squared. All right, 4 squared, or Fg, at 1 divided by 16 equals 600 newtons divided by 16. So that's going to be 37.5 newtons. All right. And we could calculate the mass, too. The mass would be the same in both those situations. Mass of the person, the amount of stuff is the same here as it is here, but their weight changes. So considerably lighter if you're 3 Earth radii above. You're pretty far from the Earth at that point. 37.5 newtons, because you are now 4r away from the Earth compared to being r away. So you are 4 squared, or 1/16 the weight. All right, let's try another problem. Let's say we have 3 identical masses. A, B, and C. Let's make C over here. Let's say the mass of A equals the mass of B equals the mass of C. And let's say the distance between these two are 3 meters. And this is between these centers of masses, between the centers, this is 15 meters. All right, so 15 meters, and the force of gravity, this one is pulling with 0.03 newtons, and this, of course, this also must be pulling with 0.03 newtons. Newton's third law says if one pulls on the other pulls on the other, and those are the force of gravity between these must be very massive objects. The question is, what is the force of gravity between these? Force of gravity of C on B, and force of gravity of B on C. They're going to be equal to each other in magnitude, opposite in direction. Why don't you take a moment to figure out what those are?
Pause the video now.
All right. So let's see. What we need to realize is that these are 5 times farther apart than these were, okay? 3 times 5 is 15, so these are 5 times farther apart, and if the force of gravity was 0.03 newtons, the force of gravity here, let me just erase this, force of gravity of C on B equals, these magnitudes are going to be the same. These are vectors, of course. Force of gravity of B on C. They're going to equal to each other. And they're going to equal 0.03 newtons divided by 5 squared. Inverse square relationship. They are 5 times farther apart. Therefore, it's going to be 1.20 times 10 to the minus 3 newtons. Let me get that out of here. All right, so 1.2 times 10 to the minus 3 newtons. So the force of gravity is 1/25.
Extreme physics.